logarithm. Let's relate it somehow to exponent. Now, I thought these examples may lead you into what this is all about. I'm going to list a few examples of expressions being raised to an exponent, like 4 raised to the 0. We'll call that 1. I have another one here, 5 squared. It's basic. That's 25. Expressions being raised to an exponent. 3 raised to a -1. No problem. 130. 3 raised to a -2. No problem. 190. 5. 16 raised to the 1/2. No issue. 4. Number 6. 32 raised to the 2/5. Could be an issue. Now the others, the first 5 I listed, guys, I think everyone would agree with those answers. 5 squared is 25. 16 raised to the 1/2 is 4. It says square root 16. Does anyone think they know what 32 raised to an exponent of 2/5 might be for an answer?
4.
I heard 4. Can you tell me what you did? How did you translate it?
I don't know what it's called, but the root of
Fifth
root and then multiplied by 2.
Not multiply, raised.
I mean raised by 2, sorry.
That's what it means. Take the 5th root, that bottom number tells you what root to take. Take the 5th root of your base, 32, and then square it. And the bottom number tells you what root to take. The 5 in this case, my top number there, that exponent tells me what to do with it afterwards. In this case, to square it, and you end up with 4. Another one here, just another example. I brought in this one. 4 raised to a -5/2. And first, with that negative sign attached to it, I know that can be quickly written as 1/4 raised to now positive 5/2. If I use what Jonathan just suggested, he says, Professor, I think this might mean, Jonathan, tell us what it means again.
This would be the square root and then to the power of 5. You write it outside or inside.
Right, I'm gonna do mine like that. Take the square root of 1/4, which translates into, asking you to do, and then raise it to the 5th. Guys, we know what this is. This is what, 1/2 raised to the 5th, 1/32. You said, Professor, that makes sense. You took some expressions, raised them to different exponents. You raised something to a 0, raised something here, raised something to a positive, raised something to a negative, raised something to a fractional exponent. I threw a variety of numbers there to work with. Now, what I want, though, before I had a student read the definition of a logarithm, is that each one of these, and we'll be very patient with this, each one of these expressions can be written in logarithmic form. Let's get accustomed to the form, and then I'll have a definition written ready for us. Guys, I'm associating logarithm with exponent. My exponent in my first example is 0. Now, how am I going to express this with the word log or logarithm? I'm going to write this as log. The exponent is equal to 0. Notice I left a little space. All I'm saying right now, the exponent in that first expression there in the black is 0. When does that happen? When the base was 4, the base will be written as a subscript of my number 1. So this in the red, get accustomed to it, means the black. They mean the same thing, written differently. The next one, log, and I associate exponent with log, I do, that's a 2 in this case. When does that happen? That happens when the base was 5, and I had a 25. So log log base 5 plus 25 equals 2 is the same in black. 5 squared equals 25. So they're saying the same thing. This one, log, a little space here, the exponent is -1, that's what the log is. When does that happen? When the base was 3, and my expression to work with was 1/3. So log base 3 of 1/3 is equal to a -1 is saying the same thing as the black. Each one of these. Let me jump down to this one, log. In this case, of course, it's -2 for the exponent. That's 3/1/9 to work with. And here's log. In this example here, the exponent was 1/2. That's what the log is. When is that happening? The base was 16. I had a 4. The last one up here, or not last one, this one up here, log, right, the exponent was 2/5. And the base was 32. 4. Last one, this would be log, or the exponent in this case was -5/2. And when was that happening? When I was using a base of 4 on this one. Where was it? Was it base 4 here? Of what, 1/4? What do you want to do here? Oh, you want one of the 32s. Down there. And that's saying the same thing as the original. A little different. Amazing that you can, in your mind, if you know what this association is, that you all of a sudden you look at this, and in your mind, it looks like this. You have to go from one to the other, one to the other, one to the other. That's why I like to associate the word logarithm with exponent. Actually, that's what it comes down to. And that's why I threw these few examples in. And guys, on this setup here, number 8, I guess it is. Right before the break, we saw the number E. If I did this, E raised to 0 is equal to 1, which it is. And I say, now write that in log form. You say, well, Professor, if you write in log form like we're doing the others, the exponent is 0. And when is that happening? When the base was E of 1. True? Yes.
Is E also ln, or is that?
Do we get now?
Is E also ln?
That's exactly where I'm leading you to. Now, since this last one comes up so often, that base E, they love to use base E, base E, base E in the higher math. They use it so much, they abbreviate. Log base E was a different abbreviation for log, not LOG. They use LN of 1 is equal to 0. So if I see the LN notation, the abbreviation for log, it's understood to have a base E. It comes up so often in higher math. So they choose LN, understood to be a base E for that log. Okay? Basically, that's what we're doing with a log. If I should throw this one in, if it comes up, number 9. If I have 10 raised to a -2, 10 raised to the -2 is 1/100. No doubt about that. But what does that look like in log form? It looks like this with the association here. The log or the exponent is -2. The base was 10, and my number was 1/100. That's another one that comes up quite often. And sometimes you'll see in textbooks where they'll drop the base and they'll rewrite this without the 10 and just write it as log 1/100 is equal to a -2. And all of a sudden you say, Professor, what's the base? It's missing. If it's missing, it's understood to be 10. And they call this a common logarithm. So we've got natural logarithm. I should use that word here. A natural log. Of course, the other one is a common log. And that's what this chapter sort of closed down with. We'll close down with. Yes?
Isaac, if I take a picture really quick for the board.
Take it. I should take credit for this. Okay, okay, guys? Now, I need a volunteer. Would someone now tell me, this is my little description. Intro, logarithms, exponents, exponents, exponents. Now, if I say exponents, you notice we'll finally get back to exponentials. Somehow there's a connection back to exponentials here. Now, can I get a volunteer to read from the handout, what that definition is for a logarithm? Any volunteers from the handout? Definition of a logarithm? Maybe a few extra credit points? Oh, still no volunteers. Oh boy, after you see that test tomorrow, you'll say, I wish I had placed my hand up and I would have volunteered. After you see that test. You need that extra credit. Go for it.
So, section 4.2, right?
Yeah, the definition of a logarithmic function.
So, there it is. Okay, so, the definition of a logarithmic function, y equals log base a.
Okay, hang on. Y is equal to log base A of x, I guess.
Yep. And then if and only if x.
We gotta use this if and only if.
Okay, and it's only if x is equal to a to the power of y. So then a also must be greater than 0.
Restriction, if A must be greater than 0.
Cannot be 1.
Hang on now. Go back here, same thing. A must be greater than 0. So let A be 1, be greater than 0.
And the domain of y equals log a x is greater than 0.
That's the x. That's my domain.
Yep. Then if the base a is the number e, y equals log e or log base e x equals a natural log of x means that e to the power of y is x.
Beautiful.
This-
I mentioned that on the natural log earlier. Absolutely.
And then this function occurs so frequently that it is given the symbol ln.
Now, he was asking me during the break, he says, Professor, I know I have a little knowledge of E and ln, natural log, natural log, natural log. And other students have seen natural log. And he read right in the statement there, it shows up so often, something to that effect. It's used so often in higher math. I used it in grad school, a lot of it in grad school. Why do they choose ln base E? Mr. Park? Arena's busy with her notes there. Could you do a little research and maybe, who you wanna ask, Alexa or Siri or somebody? Something about natural log. Why are they using natural log? See if you can find some, do a little research for us. Why is natural log used so much rather than common log? Why do they love to use ln? So we're gonna try to we'll find some history of that. And let's know, why are they using ln so much, which they do. These calc courses are full of lns. Natural logs. Very seldom will you see a log base 10.
It says natural log is used because they naturally arise in many mathematical, physical, and real world.
I'll read a little louder.
Yeah, such as exponential decay and growth, and the derivative of ln x is simple.
Okay, so it has something to do with exponential growth and decay, which we have not looked at yet. Exponential growth and decay. What else do they say?
And it appears in statistics and machine learning.
Oh, you can also use this in stat courses.
And the inverse of ln x is
And then they say something about the inverse.
yeah, and then it's some derivative, e to the x.
Definitely, okay. The derivative of e to the x, what was the derivative of e to the x?
E to the x.
It gives you takes you right back. That's unusual. If you use a calc procedure, like a derivative, you take the derivative of e to the x, he says, Professor, the answer is e to the x. Its derivative is itself. That's unusual for a function. Okay, so that's to sort of help you answer your question? Okay. So guys, that's e raised to the x. Now with the log here, whoa, or ln here, and with all those restrictions, not too many restrictions, this base has to be greater than 0, don't let it be 1. The number here, this is strange. That number, which is the domain, has to be by definition greater than 0. We're not going to try to take a log of a negative number. That's out. If you look back on my examples, I didn't have that happening over there. And also, you cannot find log of 0. So the domain inside there must be greater than 0. So in other words, guys, I know it's unusual, but look at this. Log, I'm going to use base 2 maybe. This number is impossible. Undefined. Here's my restriction on the domain. Must be greater than 0. I can't even do this. Seems like we should be able to, but we can't. Log base 2 of 0. Undefined. Can't do it. Now, can someone tell me, I see by the definition why, because the restriction was x must be greater than 0. Can someone tell me what this really would translate into, with my description over here, what would this really say if you try to translate it? Log of 0, base 2, in your mind, what does that mean? What can you visualize there? Yes? What can it look like? Anybody? Or about it?
0 is not in the range of the two exponents.
I got you there, but tell me in your mind right now though, someone says log of 0 base 2, tell me based on what we're doing over here, what does that look like in your mind, and then we'll see what's wrong with that. Yes?
2 to the x cannot equal 0.
Okay, 2 raised to something is supposed to be 0. Is that what that actually translates it into? Because I don't know what it is, so you put an x over here, and she translated that for me. Is that means 2 raised to the x equals 0? And you know you cannot raise 2 to anything to get 0. If you raise 2 to 0 itself, you get a 1. So there's not a real number out there that you can raise 2 up to for an exponent to get 0. So that's why this is out. You can't, same thing about negatives, you can't get negatives. So I'll have to accept this definition and the domain on this. Okay? Now, I think on the handout, with that said, I'm going to do this. Let's see, what am I going to do here? We'll try this. I would like to graph a log graph. Did I do a log graph right before the break? Did we see a log graph? No, I don't think we've done a log graph yet. It's time, and then we'll take a look at some of these examples from your handout. And then also I got to pass out the more review for that test. Okay, guys, let's call this part 2. Try to use this. And I would like to sketch this. Y is equal to, or f of x, is equal to log base 2 x. Let's see what it looks like. Please remind me though, before the break, did we do 2 raised to the x? Did we? Now this one says log of x base 2. Okay. Now, with that said, I like to graph it. Now, did I approach the graph before the break with a table? Did we actually construct a table and put some numbers in? I'd like to also try it here, since it's new for many students probably. Why not use a table? If I can. Now, what can I place in the x column? What can I get for the y column here, guys? It says log base 2 of x. Now, I think the restriction on the x is it's going to be greater than 0. So that means in my x column, maybe try some numbers that might work out nicely for me. I can try 1, I guess. Maybe a 4. That's not too bad here. Try and come to some numbers here. 16. Let's try those 3. See, that's enough. Make the point. Guys, if I put a 1 in here, it says log base 2 of 1. What is the log of base 2, 1. Zero. Says 2 raised to what will give you 1? It's 0. I'll plot that here shortly. Now I'm going to put a 4 in here. Now it says log base 2 of 4. Translated in your mind, based on this over here, it says 2 squared. That's 4. I put a 16 in there. Log base 2 of 16 is? 4. 2 raised to the 4th is 16. Now I tried only 3. You tried others, of course. I tried to come up with some reasonable numbers there. I don't know, but we'll see. When I plot this, those 3, we'll see what it might look like. And this. Okay, guys, I'm gonna plot it. Here we go. Out 1, 0 is here. Out 4, up 2. Oh boy. 2, 3, 4. I'm just do a rough sketch. Say out 4, up 2 is in there somewhere. Out 16, way out there is up 4. So it's rising with the number of points I have. Now what may help me though, and I don't have those in my table, the restriction was that x, domain, had to be greater than 0. Well, those I chose, 1, 4, 16 are greater than 0. How about 1/2? 1/2 is greater than 0. So could I have placed in that table for some reason 1/2? Now can anyone tell me what the log of 2, be careful, log of 2, base 2, log base 2 of 1/2? -1. So that would give me a -1 to work with, which may help me in this attempting to graph. So guys, now I have a new point to work with, out 1/2, down 1. So it's down here somewhere. 1/2 down 1. And I can plot additional points. Is that enough, do you think, to get the shape I'm looking for or not? And with those only 3 points there, might the shape be, it's in red here, something that looks like this? Even with those few points I have connected, might it look like that? Miriam, I think before the break, now I'm going to accept this red graph as the graph of y is equal to log base 2 x. I think before we took a break, I had a graph, I think, I recall, that looked like this. I think. Which was named as, if I'm not mistaken, an exponential, maybe that. Is that true? Does anyone see a relationship between that red and blue? Is there a relationship? Or better yet, maybe I should do it this way. Let's go to the red graph. The red graph represents the log. Its domain, if I accept that red graph, the domain of that red graph, the log graph, is everything to the right of 0. The range of the red looks like it's -infinity through +infinity. Gotta make sure, see what I'm doing here. The blue one, its domain up here was this, on the blue one before the break. The range on the blue one was this. Now, does that give you a hint, maybe, what's going on here? Are the inverses. The domain and the range interchanged. So it looks like I have an exponential, 2 raised to the x, then a log base 2 of x are inverses of one another. So an exponential and a logarithmic function are inverses. looks like they are based on the domain and range. The domain and range switched on us. I've got all that set up here for you now. With that said, hold on, just a minute here. If they are, which they are, inverses, to check it, you're supposed to do this. And you're supposed to get that. Did we not discuss that before the break? Form the composite of a function with this inverse, and you're supposed to get x if they are inverses one another. We're saying these two are. So guys, in this case, let's try to find f of the inverse. And try to show it's x. Okay, that's gonna be a little strange. Now, which one do we want to accept as the inverse? Which one would we like to accept as the original function? I will take the log graph. I think this is one in red I did. That's log graph. Let's assume that's my inverse. And then we've got the blue one to do a composite on it. So inside here, guys, I'm going to use the original function as this. Its inverse is, we think, 2 raised to the x. So we put 2 raised to the x in there. Like this. Straight. And got f of that. Which now means go to the other graph, my red one, make a replacement, and write this as f of 2 raised to the x looks like in red, this, log base 2 of 2 raised to the x. Do we agree? Is that the way it looks if I place one function into the other? If these two are inverses, the answer should be x. That's where you check a function with its inverse. Log of 2, base 2, log of 2 raised to the x. Base 2 is merely x. Based on this we're doing here. Now, can I do this in general here? Log, let's say base a raised to the x. Can I always just get an x? This looks so much like this. Do you think this should be a general statement? Can this always be true here? Should it work out? In other words, now, if I ask you to take the log, let's say base 4, 4 to the 5th, should the answer automatically be 5?
Yep.
If I accept that statement. Could I do, I'm bringing one more. Could I do an ln, that's a natural log, let's say e raised to the 10th. What can I say the answer is? 10. Really 10. Based on this discussion here, which led me to this. So if I see something that looks like this, I can say x. Okay, so that's the relationship between those two. Now, with all that said, I'm getting close here to look down so I can do more review for that test tomorrow. Let me think. Hang on. See if I got something else I would mention about this. Maybe I'm finished with it. Okay. Nice. Murray says this is when we're closed down. Guys on the side here, my students are doing the homework. Professor, I follow you. I understand your relationship between the logarithm, that word logarithm, and the word exponent. I see now the relationship between the two. I'm doing my homework. And my homework says, since you're thinking about this, in reference to this, I had properties back in middle school for exponents. When I had exponents as a discussion back in middle school, I had properties. So listen to this, guys. We're in class with this. Properties of exponents. from middle school. One property, you'll recall this, if you have this times this, you're allowed to add the exponents. A raised to the n times A raised to the n, where you're allowed to add the exponents in a case like that. And they call this what, I think, the product property of exponents. You solve that. If you solve this, since I'm dealing with exponents, A raised to the m being divided by, not product, a quotient. Who recalls from middle school, what were you allowed to do with the exponents in a case like this? Subtract them. A raised to the m minus n. The one that you may have forgotten, maybe not, let's see, A raised to the m raised to the n. What were you allowed to do with the exponents in a case like that? Multiply them together. Now, let me close down. You've done a good job tonight. That is, I can rename these properties from middle school now in terms of logarithms. Guys, check that handout. Did I have the properties of logarithms somewhere on that handout? If I did, I'm going to use the same notation your textbook uses. But it's going to look so much like middle school, except now it's written in terms of logarithms. I see the product property. I see it listed on your handout. Looks like this. Log base A of a product m times n. Much like this for middle school. If I see that, I'm allowed to log base A of m plus log base A of n. That's middle school, this is us. In essence, we're saying the same thing. For the quotient, log base A, and I'll write like this. And looking back from middle school, now I can rewrite this as log base A of m minus log base A of n. There's middle school, here's us. We're saying the same thing. Now notice they wrote the next property. By the way, this is the product property listed on your handout. This is the quotient property. That's like middle school. Last one's a power property, they call it. Now I think, if I'm not mistaken, they wrote this as log base A of, did they use m raised to the r? I think they did on your handout and in your textbook. If that shows up, you're allowed to, by this property, rewrite it as that. Which is much like this. You're multiplying the two together. Much like the power property back in middle school. Now guys, I don't have the time to use those properties. You guys are doing your homework. At least I've introduced the three properties of logarithms, where logarithms are merely exponents. So three properties of exponents in middle school, three properties of logarithms for us, and that's the way it looks. Now, staring at it, done a lot tonight. We always do a lot. How's this looking? Just more and more and more to remember. I realize that. You have to know what's going on here. Do not let this overwhelm you. This chapter 4 is closing down. I will tell you, Arena, Mr. Park probably will agree, the test, when you finally see a test on logarithms, which is not that test tomorrow, that one, I'm concerned about the one tomorrow also, but the one on logarithms and the exponentials, Arena, you guys had the math 2 before, that could be the toughest test. Arena, what do you think? On the logarithms and the exponentials, do you recall?
Yeah.
It was tough.
Mm-hmm.
Park?
Mm-hmm.
It was tough.
Mm-hmm.
Okay, so we'll wait to see what happens on exam number 3. I think tomorrow's exam number 2. Okay. Guys, I think we've done a good job, right? Now, I'm excited about the group work. So if I do it, and I'm pretty strict, if I do it, and we come in here on Monday, and I do my little business like I do, and then all of a sudden I look up and it's about this time, or probably earlier, I'll say, let's quit guys and go downstairs to the math lab. And Arena and Park, we're gonna have worksheets appropriate to what I did in class. And you guys are gonna work in a little group on some problems that they have for you. They're gonna collect them. And you get a few points. Right? I'm going down with you. So I know how students are. I've been around too long. I know how students are. You go down to the math lab, and I don't want to walk in there and see students in a group saying, "Hey, bro, what are you doing this weekend? Are you going surfing, bro? Oh, bro." Or the girls are saying, "Oh, nice shoes. Where'd you get those shoes? Oh, where'd you get those shoes?" We don't want to hear that. Yeah. No, we want to hear logarithms and exponentials. Forget the bro. Gee. Where'd you get those shoes? Oh, yeah. No. So when we do that, we're going to be serious about it. So they're going to work with you guys. Now, the exam coming up tomorrow. I've helped you big time. And one reason I did this, I'll be very honest with you. After I saw the scores and the way the work was presented to me, the work on the quiz, I was so impressed. I thought, whoa, the class is really working at it. They are working at it. It's maybe tough, but they're working at it. So I thought, hold on, we'll help them out. So guys, one question on the exam tomorrow would be to take a quadratic, complete the square on it. You know how complete the square is. Complete the square, wrap it, and then answer a few questions. Here's one worked out. Worked out. Then on the other side are some questions about that graph after you get the graph. You're going to have one like this. I don't think I placed the same one on your test, I hope not. So this is a little practice, and then on the other side a few questions. And then there's a couple of, how cute, word problems. Now, can anyone remind me of what could I place on that test for you guys to do in terms of word problems that you've seen in the past? What type of word problems have we done? Tell me again. Oh, you're going to create a function, okay, something else.
Quadratic applications.
Okay, now if you say quadratic applications, give me a specific example.
Like finding the maximum height.
Thank you. The maximum height when something's tossed up in the air. I don't know where this particular one, no, this is a different one, that's a typo. Something being tossed up in the air, how high does it go, how many seconds does it take to hit the ground? Can't miss one like that, that's easy. Another one though, that may take a little bit more effort. Applying or an application of what we've been doing. And I did it in class, I did an example. Yes?
Enclosing a fence around a rectangle.
Where you have to enclose a certain piece of ground with a fence, and maybe one side requires no fencing, or who knows, I may say all four sides require fencing on the test. But I think the one I did in class, one side had no fencing required, is that true? I think that's the one you're gonna see here. Now, is that gonna be nice to at least see this? And know, and in your mind, know that you're gonna have this completion of the square and an application or two. This one has just one look at, of a fencing type problem. And of course, you would also love to have one where they toss something in the air and say, find the maximum height. Those are very easy. So you're gonna have some applications here. Mr. Park, Arena,